Hey guys, what's up? Welcome back. Looks like we have a little background noise, so hopefully it'll be done here in a minute, but we'll see. The topic of today is triple integrals. It's just pretty much like double integrals, except you have three variables that you're floating around. So 15.6 today. 15.7 next time. That's triple integrals in cylindrical coordinates, and then triple integrals in spherical coordinates will be after that. So yeah, we're getting there, almost through chapter 15. And then our test is actually, I'm gonna push it to Wednesday next week because there's a engineering exam on Monday. I know a lot of you are in engineering right now, so I think we'll push that exam back to Wednesday next week instead. So but today, 15.6 triple integrals, and it's really just in Cartesian coordinates today. So triple integrals, let's just kind of recap what we know about integrals so far. It's integral from a to b, f of x dx. That was representative of the area under f of x over the interval AB. So the area under the function f of x over the interval AB. And f could be continuous, it could be discontinuous, it just depends on the function. As long as it's not too discontinuous, which we're not worried about in this class, of course. So, but yeah, that was a single integral of a single variable function f of x dx. And that was, for lack of better terms, the area under the curve. We know that it could represent other things like work and probability, expected values, things like that. But just for our introductory to integration, we just introduced it as the area under the curve. And then likewise, for the double integral over some region R, f of xy dA, that was the volume under the surface f of xy above the region R, and the region R, of course, is in the xy plane. Of course, it didn't have to be volume. We found out last time it could be mass, it could be inertia, it could be probability, it could be charge, etc. But we introduced it as volume, right? So we introduced it as volume. However, it could be any one of these other items. Now, a triple integral over some region, we'll call it E, some solid region E, f of xyz dv, what will that represent? I don't know. There's no visualization. No visualization for f of xyz. So I don't want to talk about it as some kind of hypervolume because that's dumb. So it really depends on what f of xyz represents. So it's really more of the second category. There's no go-to interpretation for a triple integral. So we need to know what f of xyz represents. To be able to interpret. Before we can interpret the integral. You know, for example, if f of xyz is kilograms per meter cubed, then the triple integral over the solid E f of x, y, z dv would equal the mass of the solid E. So a triple integral is going to need an interpretation based on the function f of x, y, z before we can actually know what we're talking about. So we could do the same kind of things. We could apply a triple integral to mass, center of mass, probability, charge, and other applications. But the approach is the same, right? We just treat the other variables like a constant. The trickiest part for triple integrals is setting them up as setting up the bounds, setting them up as iterated integrals over general regions. So the setup is, first of all, over a rectangular solid for starters, kind of like we did over rectangles for double integrals. So we have some rectangular solid and it's between A and B on the x-axis, between C and D on the y-axis, and 0 and E on the z-axis. Then we would do the same approach that we did for double integral. We would cut the x-axis up, we would cut the y-axis up, and we would cut the z-axis up into a bunch of smaller rectangular solids. And we would get a bunch of rectangular solids just like this. Such that delta V would be delta X, delta Y, delta Z. And then the triple integral over the region E, the box, f of x, y, z dv would be the limit as m, n, and p all go to infinity. And to triple Riemann sum, m equals 1 to infinity, or I equals 1 to m, I equals 1 to m, summation j equals 1 to n, summation k equals 1 to p, f of xi, yj, zk, delta v. So it's the limit of a triple Riemann sum. If we're over a rectangular solid, it's very nice and easy. So as an iterated integral, we'd have integral from, I don't know, we'll say 0 to e, integral from c to d, integral from a to b, f of x, y, z, dx, dy, dz. So it's very nice if you have a nice rectangular solid as your bounds. You just have nice constant bounds. So it's very similar to double integrals. Very similar to double integrals, not much different. You just set it up as an iterated integral and evaluate. The hard part comes when you have non-rectangular bounds, right? When you have a non-rectangular solid. Then the region of integration, you have to figure out the bounds for the region of integration. That's usually the trickiest part for triple integrals. So over a non-rectangular solid, the bounds become more difficult. To describe. So you have to really put some thought into how to get those bounds. Let's say you have a paraboloid bounded above by some kind of plane or something like that. And you have to think about those bounds and try to find the bounds. But let's just do an example where we do have a nice box first. And then we'll do an example where we don't have a box. So example, to start off, evaluate the triple integral. So evaluate the triple integral over the solid Q. And then our function is 2x e to the y sine of z dv, where the solid Q is the set of all triples x, y, z, such that x is between 1 and 2, y is between 0 and 1, and z is between 0 and pi. So this is the starter because it's just a nice rectangular box. X is between two numbers, y is between two numbers, z is between two numbers. So we have just a nice rectangular box, which is the solid Q. We're integrating over that box. And maybe this function represents its mass or something. I don't really know. Or this function represents the density. It just depends on what the function represents as to what the integral will be interpreted as. But regardless, we can just set up the integral. I'll just do, it doesn't matter. I'll do x first, then y, then z. So z bounds go on the outside, 0 to pi. Y bounds on the middle, 0 to 1. X bounds in the inside from 1 to 2. And then the function is 2x e to the y sine z dx dy dz. Okay, so it's the same as like we did for double integrals. You work from the inside out. So we're going to do the x integral first. So if we do the x integral first, well, we still have integral from 0 to pi for z, integral 0 to 1 for y. And now if we integrate x, treat y and z like constants. So that's just going to give me x squared e to the y sine z from x equals 1 to x equals 2. dy dz. And then plug in those bounds for x. So this is going to be integral 0 to pi for z, integral 0 to 1 for y. And if I plug in x squared, x equals 2, I get 4 minus 1 squared, which is 1, times e to the y sine of z dy dz. So evaluate those bounds. Get 4 minus 1. 4 minus 1 is just 3. I can pull that out of the double integral completely. So that's 3 times integral 0 to pi. And integrate with respect to y, I just get e to the y sine z from y equals 0 to y equals 1 dz. So that's integrating with respect to y next. And evaluate that, we get 3 times integral 0 to pi e minus 1 times sine c dz. And e minus 1 is a constant, so I can actually just say that that's going to be 3 times e minus 1 integral 0 to pi sine of z dz. And so that's 3 times e minus 1 times, and then the integral of sine or antiderivative is negative cosine of z from z equals 0 to z equals pi. So that's going to be 3 times e minus 1 times negative of negative 1 minus negative 1, which is 2, so that's just 6 times e minus 1. And that's our answer. Any questions? Of course, we chose to do x and then y and then z. You could actually do any order that you want. It's kind of like Fubini's theorem for double integrals. I could have done z and then x and then y, or I could have done z then y then x, or y then x then z. It doesn't matter. You get the same answer regardless of the order of integration. And when you have these nice rectangular solids, you don't really have to do a whole lot of work to switch the order of integration. If you remember back for double integrals, when we switched the order of integration, we actually, if it was a general region, we had to be super careful to change the type. You know, if it was a type 1, we had to change it to type 2 bounds. So we have to be careful when it's a general region for a triple integral. So that's what we're going to talk about now, is maybe a triple integral over a general region. So question, what about general regions? So for general regions, we have to figure out the bounds. So the steps to tackling general regions are, first, decide on an order of integration. And then determine appropriate bounds based on that order. So it's kind of like for a double integral, we need to know if it was going to be type 1 or type 2. That way we can know how to set up the bounds. That's the same thing here. We have to figure out, is it going to be z first and then y and then x? That's a common approach. Or is it going to be x first and then y and then z? It just depends on what order of integration you choose. That tells you how to set up the bounds for a general region. And a lot of times there's a best way to do it, and sometimes there's no good way, or they're all equivalent. So they're all the same as far as the setup goes. It's not going to be any more work to set it up one way than the other, and likewise to do the integral. But sometimes there is a better way to set it up. Sometimes it can't even be set up like x first and then y and then z. You have to do z first. It just depends on the problem, to be honest. So the more practice you get, the more you'll kind of get the knack of doing this. So example, I evaluate evaluate the triple integral over the solid Q, and the function is 6xy dv, where Q is the tetrahedron bounded by and we have some planes here. So bounded by the planes x equals 0, y equals 0, z equals 0, and 2x plus y plus z equals 4. So we'll call that part A. Part A is evaluate. Part B is set up the other 5 orders of integration. So I'll show you in part A the best order of integration in my opinion, and then in part B I'll show you the other 5 orders of integration that we could have set up. And regardless, you'll get the same answer, but in my opinion there's one that's a lot easier to set up mentally, physically, actually doing the work. Alright, so let's see what this tetrahedron looks like to begin with. So just draw my 3D space here. And let's see. If y and z are both zeros, x is equal to 2 for this plane. So say x equals 2 is like right there. And if x and z are both 0, y is equal to 4. And if x and y are both 0, z is equal to 4. So that kind of tells me what this plane at the very end looks like. And because I'm bounded by the coordinate planes, I'm actually just up here in the first octant. So this is what this plane looks like. So that's our tetrahedron right there. And I'll just draw the bounding lines. And in my opinion, part A, the best order, my preferred order of integration is z first, y second, x third. Because to me, that's kind of almost like a type 1 integral for a double integral, because we're doing y and then x. So x is ultimately going to be between 2 constants. Y may be between 2 functions, but x is going to be between the constants. And that, in my brain, I like type 1 integrals the most. So I'm going to do z first, so I can basically get to a type 1 integral for x, or for x and y. So now I've got to say, okay, what are the bounds for z? Where is z going? So what are the bounds for z? Z seems to start at 0 and go up to the plane. And as you get further and further back, you get taller and taller. So the bounds are going to be 0 less than or equal to z less than or equal to the plane. So I've got to take this plane equation right here and solve it for z. So that's z equals 4 minus 2x minus y. So that's my upper bound for the z direction, 0 less than or equal to z less than or equal to 4 minus 2x minus y. And then I say, okay, that's my bound for z. Z is bounded above by the plane and bounded below by the xy plane. Now, for what xy values am I doing that for z? Well, everything down here in this triangle, this pink triangle, are my bounds for x and y. So for x and y, I'm going to draw it like this. I know on the y direction it's at 4, and on the x direction it's at 2. And I have this triangle here in the xy direction. And I'm trying to make all the colors match up so we can kind of see. Okay, that's my xy bounds now. So I've got to determine the xy bounds based off of that. So the xy bounds, I'll say, like I said, I'm going to do x at the very end, so x is going to be between 0 and 2. Y is going to go from 0 up to this line. So 0 less than or equal to y, less than or equal to the line. So what's that line equation? Well, that's actually where the plane intersects the z equals 0 plane. So actually I could just plug in z equals 0 to this plane, or I could find this straight line equation using the slope and the intercept and all that stuff. So I could actually say this line is y equals negative 2x plus 4. So that's my upper bound for y, negative 2x plus 4. And I've got my bounds, so now I can do the triple integral. So then I've got integral 0 to 2, integral 0 to negative 2x plus 4, and then integral 0 to 4 minus 2x minus y. And the integrand itself is 6xy, and then I'm going dz, dy, dx. I guess I may not bore you with all of the details, but I'll just do maybe the first variable here. So integral 0 to 2, integral 0 to 4 minus 2x. I'll get 6xy z from z equals 0 to z equals 4 minus 2x minus y, dy dx. Plug in the bounds, keep going. I think eventually we get to 64 over 5. So it's just an iterated integral at this point. And you keep plugging in, doing the polynomial stuff. It's not too bad. Again, like half the work, at least half the work, is setting up the bounds correctly. You know, just understanding what's going on, setting up the bounds correctly. So, any questions so far? It's just part A, doing the integral the easiest way that, in my mind, the easiest way I can think of. Any questions so far? Okay, so that was part A. Part B. So part B, we just have to do the other 5 orders of integration. So the next one that's very similar is we could do z first and then x and then y. So it's almost the same setup, but I'm just doing a type 1 whenever I get to x, or type 2 instead for x and y. So z is still the same, 0 less than or equal to z less than or equal to 4 minus 2x minus y. But now, if you look back at our triangle that we have here, draw it again. That was 2, that was 4. So look back at this triangle in the xy direction, and this time we're doing x from 0 to the line. So 0 less than or equal to x, less than or equal to the line. And y is actually going to be between 0 and 4. So 0 less than or equal to y less than or equal to 4. So what was that line equation? Well, we already said it was y equals negative 2x plus 4. So basically, if I solve that for x instead, we could say that that's x equals 4 minus y over 2. So that's the line equation. So I'm going to replace that line with 2 minus y over 2. And so then our triple integral could be represented as integral 0 to 4 for y, integral 0 to 2 minus y over 2, integral 0 to 4 minus 2x minus y, 6xy dz dx dy. So that's the first of 5 that we have to set up. So that would be setting it up with z, then x, then y. All right, so that's one. Let's see, another one we could do. Let me just kind of label these. Call this one the second. We'll do a third one. Let's do, I don't know, we'll do y first. And then, so we'll do y first, and then we'll do z, and then we'll do x. Okay, so let's go back to the original 3D image. And our tetrahedron looked a lot like this. And if we are doing y first, we can actually say in this case now, if we're doing y first, that y goes from 0 to the plane. So if we're doing y first, I'll say that y goes from 0 to the plane. And let's just remind ourselves of what the plane equation was. It was 2x plus y plus z equals 4. So what I'm going to do is solve the plane equation for y. So that's going to be y equals 4 minus 2x minus z. So that's my upper bound for y. That plane equation, 4 minus 2x minus z. Okay, you might say, okay, well, that's cool, but for what xz values is that happening? Well, that's happening for all the xz values in this triangle here, in the pink triangle. So let's draw that in the xz plane. So in the xz plane, I just draw x going this way, z going up. It's kind of the same thing. Z is up here at 4, x is over here at 2, and there's a triangle there. And we said we're going to do z next, so z is going to go from 0 to the line. So 0 less than or equal to z less than or equal to that line, and x is going to go from 0 to 2. And what's that line equation? Well, that's going to be the line z equals 4 minus 2x, right? It's got an intercept of 4, a slope of negative 2. Again, you can find that as the intersection of this plane with y equals 0. So that's the line that bounds with z above, so that's the upper bound for z, so 4 minus 2x. And so our triple integral can also be expressed as integral from 0 to 2, integral from 0 to 4 minus 2x, integral from 0 to 4 minus 2x minus z, 6xy, dy, dz, dx. So that would be another representation. So that's 3 out of 6 so far. Well, from here we could just do the same thing but swap x and z, and that basically turned it into a type 2 for this setup. So number 4 would be very similar. Any questions so far, though? Okay, I may skip the next one, the fourth one. So I'll just write it. The fourth one would be do y first. So first do y, then do x, and then do z. So I may skip those because it's very similar to just changing the order of z and x here. And I believe you should get something like integral 0 to 4, integral 0 to 2 minus z over 2, integral 0 to 4 minus 2x minus z, 6xy dy dx dz. So that one's very similar. You just switch the order of x and z from the previous one. The fifth one, I'll call it, would be to do maybe x first, then z, then y. So again, we'll draw the three-dimensional region, tetrahedron. Two, 4, 4. Draw the tetrahedron again. Whoops. And now we're going to do x first. And I'll say that x is going to go from 0 out to the plane. So 0 less than or equal to x less than or equal to the plane. And what was that plane equation? It was 2x plus y plus z equals 4. So what we're going to do is solve that plane equation for x. So x equals 4 minus y minus z all over 2. I'll just leave it like that, I guess. So that's our upper bound for x. 4 minus y minus z all over 2. And then we ask ourselves, okay, for what y, z values is x going from 0 to the plane? Well, for every y, z value in this triangle here. Of course, we know this is y equals 4 and this is z equals 4. So now let's draw that triangle in the yz direction. Whoops. So in the yz direction, whoops. We have y, we have z, but now both of them are 4. So the line equation is going to be a little different. It has a slope of -1 now. So this is the equation z equals 4 minus y. So that's the equation z equals 4 minus y. So y is going from 0 to 4, while z goes from 0 to the line. So the line, 0 less than or equal to z less than or equal to the line, and then 0 less than or equal to y less than or equal to 4. And that line equation is now 4 minus y. Z equals 4 minus y. So write it 4 minus y. And we get the integral from 0 to 4 for y. Integral 0 to 4. Integral 0 to 4 minus y. Integral 0 to 4 minus y minus z all over 2. 6xy dx dz dy. So that would be a 5th order of integration, and the last one would basically, in this scenario, to switch y and z. So basically turn it into a type 2 where x is first and then y and then z. So I may skip that and just go ahead and give you, if you do x first. So the first one you do is x, the second one you do is y, the last one is z. You get to the setup, integral 0 to 4 for z, integral 0 to 4 minus z, integral 0 to 4 minus y minus z over 2, 6xy dx dy dz. And that's it. That's our 6 orders of integration. Like I said, in my mind, it's easiest for me to think of z going from somewhere down to somewhere up. I can think about the other orders of integration, but for me it's easiest to do z first and say z is between 2 variables. In this case, the xy plane and the slanted plane. But it's possible, to set it up as other orders of integration. So it just depends. Just depends on what you prefer or what you see or whatever. So, any questions? All right, let's do another example. It's going to be a little bit harder. The region of integration is going to be a little more complicated. So example, find the volume. Find the volume of the solid bounded by the plane x plus z equals 4, the parabolic cylinder z equals 4 minus y squared, and the planes x equals 0 and z equals 0. So what a mess. What a mess this is going to be. One thing we want to note before we get into this. So note, just like the double integral of some region R dA was the area of the region R, likewise, triple integral over the solid E, 1 dV is going to be the volume of the solid E. So all we have to do to find volume for some crazy three-dimensional region is not necessarily do a double integral, but we could set up a triple integral where the integrand is 1. So we could set up a triple integral integrand of 1 to find volume, just like we could set up a double integral integrand of 1 to find area. We could do a triple integral of integrand 1 to find volume. Because at that point, your triple sum, your Riemann sum, you're not multiplying by any density function or anything like that. You're just adding all the volume elements together. So your triple integral then represents volume of the solid. All right, so solution. Let's graph it and then decide on an order of integration. So let's graph this thing if we can. Let's see what happens. So we're bounded, we know, below by the xy plane, z equals 0. So let's draw a parabolic cylinder maybe first. So our parabolic cylinder. Nice parabola. Actually, it looks more like a semicircle when I do that, but oh well. So we'll say that's our parabolic cylinder. And we want also x equals 0. What's x equals 0? That's the yz plane in the back, so we've already kind of stopped there. The z equals 0, that's down here, we've already stopped there. And now this plane, x plus z equals 4. Well, how did I know the parabolic cylinder was going to look like this? Well, if y is equal to 0, I have a height of 4 on the z-axis. And as z moves out to 2, or sorry, as y moves out to 2, z goes to 0. So this is 2 here, and this is negative 2 on the y-axis. So in the yz direction, you just see a nice parabola opening down. So if I draw just the yz direction, it's a nice parabola opening down. Height of 4, y is between negative 2 and 2. So basically looking straight at it from the x direction, you would see that cross section. Now, how do we plot this plane of x plus z equals 4? So x plus z equals 4 looks like a straight line. You could say that's z equals 4 minus x. So it would go from there to, I don't know, we'll say this is x equals 4 right here. From 4 here, so it's like a straight line coming down this way. So it's kind of cutting into the parabolic cylinder on its way down. So it's like slicing off the top of the Twinkie at an angle, starting at the back and ending up at the front. So it's like we shaved off part of the Twinkie at the top. So, my goodness, how do I draw this together as one solid? I think it's going to look something like this, if I can draw it correctly. So back here we've got this nice parabolic cylinder. And then we know we come out this way. And here it goes straight down. And so it looks something like that. Or this front face is completely flat. So this is the plane. This plane right here is completely flat. And so that's the plane x plus z equals 4. All right, so from here, probably I think what I want to do is do x from 0 to the plane. So I'm going to say x is going to go from 0 to the plane. So back here all the way out to the plane. So I'm going to do x, then z, then y. It's going to be my order of integration that I think that I'm going to choose. So 0 less than or equal to x less than or equal to the plane. 0 less than or equal to z less than or equal to the parabola. And then -2 less than or equal to y less than or equal to 2. So I think that's the order of integration I'm gonna use. That seems to be, in my mind, what's gonna work out best because of that flat plane kind of going at an angle in the xz direction. So let's do this order of integration. So x is going from 0 to 4 minus z. Z is going from 0 to the parabola, which was 4 minus y squared, and y is going from -2 to 2. So then volume is going to be integral -2 to 2, integral 0 to 4 minus y squared, integral 0 to 4 minus z, dv, so 1 dv, so it's going to be dx dz dy. We didn't really discuss the yz bounds in depth, but let's go back to this picture here. Z is going to go from 0 to the parabola, while y goes from -2 to 2. So -2 less than or equal to y, less than or equal to 2, and 0 less than or equal to z, less than or equal to 4 minus y squared. So those are the yz bounds that we're considering, such that x is going from 0 out to the plane that's basically in our direction as we're looking at this yz plane. So the x direction points straight out at our face, which is where the slanted plane is coming towards us. And for all x values along that direction, they're coming out of this parabola region. All right, so now we just have to plug and chug, do the integral. So this is going to be integral -2 to 2, integral 0 to 4 minus y squared. Integral of x would be x, or sorry, integral of 1 would be x from 0 to 4 minus z, so that's going to be 4 minus z dz dy. So doing the x integral, we just get 4 minus z. Now doing the z integral, we're going to get integral -2 to 2, 4z minus z squared over 2 from 0 to 4 minus y squared dy. And so plug in the bounds. This is going to be integral -2 to 2, 4 times 4 minus y squared minus 1/2 times 4 minus y squared quantity squared dy, which is going to be integral -2 to 2, 16 minus 4y squared minus 1/2 times 16 minus 8y squared plus y to the 4 dy. And now let's just simplify. So this is going to be integral -2 to 2, 16 minus 4y squared minus 8 plus 4y squared minus y to the 4 over 2 dy. And we get some nice cancellations here. 4y squared goes away. It's nice. 16 minus 8, that's just 8. So this is going to be, and it's actually an even integral over a symmetric interval. So I can say this is going to be 2 times integral 0 to 2, 8 minus y to the 4 over 2 dy. And that's going to be 2 times 8y minus y to the 5th over 10 from 0 to 2, which is going to be 2 times, let's see, 16 minus 32 over 10. So that's going to be, let's see, what can we factor? I can factor out a 16 from that, so it'd be 32 times 1 minus 1/5. So 32 times 4/5, so 64, 128 over 5. So 128 over 5 units cubed, because it's volume. I didn't tell if it's like meters or whatever, so it's just a units cubed since it's a volume. So 128 over 5 units cubed. Any questions? All right, if there are no questions, I think we'll call it a day here. Yeah, just start to get some practice. It's so similar to double integrals as far as the evaluation goes. Just now you're setting up 3 sets of bounds, or 3 variables. So you have to set up the bounds for 3 variables. That's a little bit more tricky. You have to visualize it a lot more. It's a 3-dimensional shape. So you really have to get some practice trying to graph these 3-dimensional shapes yourself. So that's kind of the hardest part, in my opinion, of triple integrals, is setting up the bounds correctly. Once you get the bounds, you still have to know how to integrate, of course, but hopefully it feels easier from that point forward. So hang in there. I think it should be okay for everybody, as long as you know how to integrate once you get the bounds set up. So really get some practice visualizing, setting up the bounds. That's going to be your bread and butter. And then you just have the icing on the cake after that. So just do the integration. So cool. Well, have a good afternoon. I'll talk to you guys later. See ya.